So in this video, I'm going to do a step-by-step calculation of flux. So I'm going to give you the recipe, what steps to follow and in which order. The same thing I said when I gave you the recipe to calculate a surface integral is that this recipe is great for beginners so that you don't get lost and you make sure you didn't forget any step. But once you have done many problems, it's perfectly okay to don't follow the recipe. I mean, this recipe makes the process seem longer than it actually is. So once you have experience calculating fluxes, it should be faster than having to follow all the steps one by one. This is only very useful for beginners, okay? So let me give you this beginner's guide to calculation of flux. So step to calculate flux. So our aim is to calculate this flux integral. And this is always written in the same way. We have a surface integral of a vector field, which is a vector, dot ds. And ds is now a vector, as you know, okay? So first step, parameterize the surface. This is the same first step as for calculating double integrals. So you need to find r as a function of two parameters, u and v, okay? Which is equivalent to finding, as always, x of uv, y of uv, and z of uv. And also don't forget in this step to give the limits of integration for u and v, yeah, for the two parameters. So find the limits of the two parameters that span the whole surface. Second step would be to find ds vector. And this is extremely similar to the second step in normal surface integrals, where you had to find ds as a scalar. And there are three ways of doing it. The first way is geometrical intuition. And geometrical intuition often involves reasoning which direction is ds. Pointing in. Yeah, and I can use the scalar ds and add a unit vector. For example, if you are doing a flux on a sphere, so you have this sphere. So you already know what ds is, the scalar ds, right? So you know that the scalar ds is r squared sine theta d theta d phi. That's the scalar ds. So what is the vector ds? It should be very easy because the vector ds is just a length. The length is the same as the scalar ds, but it's pointing in the direction normal to the surface. And what's the direction normal to a sphere? It's the er hat unit vector. Okay, so therefore the vector ds will just be given by the same equation as the scalar ds, but with an er hat vector at the end. Okay, so this is an example of using geometrical intuition. Okay, the second way of calculating ds is to look it up on a table or online, or whatever method you can look it up. And I've got good news for you. If we go back to the table that I said I give you in the exam, so when I explained you how to look things up in this table, I told you that don't be alarmed by the fact that ds is a vector, because we were only interested in the length. So now actually this comes up very handy, because this ds vector is exactly what we want. Okay, so for example, if we are in the surface of a sphere, we know that we have fixed the radius, so dr is 0. So we are in spherical coordinates. We set dr to 0, so this goes out, these two terms go out, so we are left with this term, which is exactly the ds vector of a sphere. It's the same scalar ds in the direction of the radius, er hat. Okay, so in this way you have all the possible ds's for cylinders and for spheres, including the direction. Okay, so this table should be great now, very useful. So that is the second method to find ds, by looking it up on a table. It works for typical surfaces. And then there is a third method, which is to apply the mathematical recipe, or to calculate it. And this will be necessary if I give you some strange parameterization of a surface, which is not in the tables, and it's not possible to find ds by geometrical intuition. Then you will have to calculate it, and you just use the formula ds is equal to the partial derivative of r with respect to u cross the partial derivative of r with respect to v. This will be a vector times du times dv. Okay, so that's the equation to calculate ds. Now, the third step is the same step as the third step for calculating surface integrals. So I call it the same. I call it evaluate the integrand at the surface. But the contents of this step, you have to be careful because you have a dot product. So what is the integrand? So the integrand is whatever is inside of the integral. So this is the integrand, f dot ds. Okay, so you need to evaluate f dot ds. You need to evaluate it at the surface. Okay, so if there are any x, y's, and z's inside of f, are there any x, y, z inside? You need to get rid of those. You need to substitute x as a function of uv, y as a function of uv, and z as a function of uv, such that you end up with f as a function of uv dot ds. So that was the same as in normal surface integrals. But now we have this extra step of doing the dot product. Okay, so you have to do the dot product. And after doing the dot product, the result has to be a scalar. It has to be a scalar, maybe some function h of u and v, which includes things that happened in f and also includes whatever ds had, but then times du times dv. Okay, so you need to end up, so let me write sanity check here. Always check at the end of step 3. This is a scalar function that depends only on u and v, plus maybe some constants. But it does not depend on x, y, or z. Okay, so always check that after this step 3, you end up with some function of u and v times du times dv. And now this is ready to integrate. This is the perfect thing to integrate. So now calculate the double integral. So now you know that your surface integral, your flux integral, has turned into an integral with where you know the limits for u and v because you found that on step 1. You also know the integrand because you found it on step 3. So this is a function of u and v times du times dv. So this is just an integral that is very easy to do. Well, maybe not, or maybe yes, it depends on the integrand. But my point is that most students, when they think about calculating flux, they worry about doing the actual integral. But actually, they shouldn't worry about this. This is more or less automatic. It comes with practice. What they should worry about is that they arrived at the correct integrand. So did you do the dot product? Did you substitute x, y, z with u and v? Did you calculate the correct ds? You didn't forget this, and so on, okay? Did you use the correct limits? Did you parameterize the surface correctly? Those, I think, are the difficulties of doing the flux. So once you do these 3 first steps, the last step is just manual, it's just the calculation of integrals, okay? So thank you very much. That is my recipe for calculation of flux integrals, and next we will do some examples.